Today we begin the second lecture of Module 1 on the conduct of research. So now we are using the second definition of that term, conduct of research. So not the behavior, but how you conduct the research. First thing I want to do is go to the WebCT on the computer and just remind everyone that although attendance isn't required, on the WebCT I'm able to monitor your last time of log on to the WebCT. So if I see that someone hasn't logged on in a while, I'll try to contact you through your lonestar@lonestar.utsa.edu email. I'll send an email to you on the WebCT, which doesn't do much good, but I want to have some means of assuring that everyone is giving attention to the WebCT portion of the course. What I have added is, widen this, a case study on plant biology, and I've taken it from this textbook on human biology, health, homeostasis, and the environment, the 4th edition by Daniel Kuras. And basically what it is the end of a chapter. Thought it was convenient, just happened to stumble upon it. And it is a point, counterpoint. I'll just show it like this. And it's on the controversy over herbicide resistance through genetic engineering. So the point is provided by Charles Arntzen, and then the counterpoint is provided by Margaret Mellon. And so I scanned this in, and it's posted as a PDF. So I'll go back to the computer and show that. So under the case studies packet here, case study A1 actually is the one I have posted at this time as my second case study. And then the plant biology case study is here. It's converted to Adobe Photoshop. I printed it out. It prints out quite all right. In Photoshop, excuse me, not Photoshop, Adobe Reader, of course, you can enlarge it to whatever % you need if you just want to read it online and things like that. On the, bring down the enlargement a bit here. On the bottom of the second page, at the end, there's challenges for sharpening your critical thinking skills. So when this gets posted, it'll be my third case study. When I post it, I'll prompt for a response to one or more of these questions, and I'll use it at the end of the lectures on the basic concepts and theories of morality and ethics, and call on you to select portions of the text or comments or points made by the authors, and to assign that to one of the types of theories that we've been discussing with. There probably won't be any right or wrong to it, but it seems like a good exercise. So be looking for that on the WebCT site. Otherwise, we begin on Chapter 2 from our textbook, and of course the challenge is whether the binding on your textbook shows that you've read up to the assigned pages yet, as I am. So I remind you that the reading assignment in the textbook is an expectation, especially in a course on responsibility. And the textbook makes some points that are really quite excellent. What we'll begin to see now is that I've created lectures that parallel the chapters in the textbook, but are not basically an outline of the chapters in the textbook. So you'll see that there are subtle distinctions between what is stated in the text and how I phrase it and present it here in the course. And the first thing that I do in the discussion on the conducting research is to talk about the skills of reasoning. I've taken this from one of the other sources, the textbooks listed on the syllabus. Actually, it's from a high school debate textbook. So the first part of this lecture is from that supplemental textbook. And I don't expect you to go and find it and try to read it or anything. I think I've extracted enough information so that you can see this. And again, what you will find is that, in essence, I'm discussing things on a more theoretical basis in these lectures that are presented, and then the practical research ethics, if you want to think of it that way, are covered very nicely and succinctly in the textbook. But as we use this course to sharpen our skills in the scientific method, developing hypotheses, and learning how to collect data, of course, design experiments and collect data and analyze data, process the data and analyze it and report it. We want to be sure that it is reliable data and we are comfortable being accountable and responsible for the data that is presented. So one of the first things we have to begin to understand is the process of establishing proof. Do we ever really prove anything in science? Or do we support our hypothesis or not support our hypothesis? Some individuals argue that when you do a set of experiments to test an hypothesis, you don't prove the hypothesis, you support the hypothesis. So a second part of the lecture that we're covering today will discuss the theoretical framework and facts, strongly supported hypotheses, weakly supported hypotheses, and so on and so forth. And we're building up to the point of talking about a research design for the related assignment. So you've got to present your conclusions to others for their consideration. So we know that conclusions are also part of any scientific report. So most of you participate in some type of a colloquium or journal club, and you have to present a paper or critically analyze a paper as you're participating in one of the sessions. And what we're going to do as we go through this course is talk about how reliable data is produced, real data is produced and analyzed, and it must parallel basically the objectives and the hypothesis of the proposed project. And that creates a logical link all the way to the conclusions. And if you develop your skills in analyzing that linkage and how it must be established, you can begin to detect in the literature, even from premier research laboratories, how they overinterpret their data and draw conclusions that are not directly supported by the data. And some of that is through weakness in statistical analysis and other things that we will establish a comfortable working relationship with in this course, such as bias and confounding factors. Basically, once you're at the point of trying to convince yourself or someone else that you can establish proof, or you're contributing to the establishment of proof for a hypothesis, you've got to present it to others for their consideration. So you make a claim, and, try to get their attention on it, and you ask for their belief in your conclusion. Okay, so this is the wording that you use in the discussion of a paper, for example, in trying to fit your study back into the theoretical framework, as you will see, and convince people that you have a sound argument for doing so. Belief in a conclusion from the scientific perspective comes from that direct linkage. If you set up the hypothesis and propose it appropriately and utilize well-designed, strong experiments where you control bias and confound and use the appropriate type of analyses, the conclusion should be obvious. There can be no other conclusions when everything is done properly, and that's the skill that we need to develop as scientists. And if you develop a good skill, as I said, you'll be able to detect how other scientists have weaknesses in that area. Very easy to overshoot on your conclusions that you draw from experiments. So you must furnish some reason why your claim should be accepted, and you have then given the other person a basis for considering your conclusion. So what we're leading up to is utilizing reasoning and evidence to provide proof for a claim. And it really parallels an hypothesis that is set up well and the experimental design that should provide the evidence fitting in with your reasoning to support your hypothesis. So it's all consistent with what we're going to be doing. So then reasoning is that process of providing reasons for the claim on the beliefs of other people. And the ing means that this is an active process and really is supposed to precede the decision or performing an experiment, another way of looking at it. The reasons are excuses that are provided after the fact. So if someone is giving you reasons, it's usually after they have done something or made the mistake and they're trying to clarify it. So you should never ask anyone for their reasons. You should ask them for the reasoning that they followed in preparing to decide or to act. And the word that doesn't show up on the recording down below is simply justification. So what is the justification for what you did? And justification requires thought beforehand, the reasoning. You must reason going into an act or a decision, and that's everything that we talked about with the theoretical and conceptual aspects of research ethics. You think it out before you make the decision or judgment or act. And it's the same thing in science. So we're kind of using that flow of thought, that general theme, to segue over into talking about research itself and conducting research. We now know how to conduct ourselves as scientists. Now let's talk about conducting the experiments, the science itself. So in establishing proof, we recognize that proof is information which, when offered in support of a claim, is considered sufficient reason to the other person to believe your claim. Now, as I said, this comes from a textbook on debate. So you're trying to convince someone to believe your claim. It's the same thing in science. If everything is linked together, as I stated, from setting up your hypothesis to the experimental design, to the way you collected your data and analyzed it and presented it graphically, pictorially, in a tabular format, whatever it is, if that is all consistent, it's easy to believe the conclusions. If there's some flaw or weakness somewhere in there, then you really have to struggle hard to convince somebody to believe your conclusions. So this is where there's a difference between debate, let's say, and science. The conclusions are always obvious. People may word them differently, but there can only be one conclusion from an experiment when it's done properly. I mean, there can be more than one conclusion, as you know, but I think you understand the point that I'm trying to make there. So it's easy to believe the conclusions from an experiment if the entire project is done properly. So if the other person fails to accept your reason as sufficient for his or her belief, then you have not proved your claim to him, her, even though he or she may understand your position better than before. So we recognize that as being part of debate, but it's the same thing in science. If you're a master's student and you're going to take your oral comprehensive exam, or if you're doing a thesis, you have to defend your thesis. Same thing with doctoral students. When you're up there and presenting fresh ideas and information, whether it's experimental or based upon your academic knowledge, you're going to be challenged like this. You may see somebody on your committee kind of look and take a deep breath. It means they don't really believe you, but they see your point of view a little bit better than they did a minute before. So you may have given a reason, but not a good enough reason to constitute proof in the mind of that person. Next, then, we've got to think of evidence in establishing proof. So it's those items of data which you have discovered and recorded during your research process and which you offer as proof in support of your claim. So you see that we're staying on a rather abstract level here, and we will get into experimental design, and the pattern will basically repeat itself. You've got to collect sound evidence to contribute to the proof of your hypothesis. Here we're talking about a philosophical argument, in essence, in the format of a debate. So without evidence, a claim has no support and is called an assertion. To assert your claim based on your own belief and nothing else. So if you present at a scientific meeting and you talk about your conclusions and your audience or a member of your audience states, so you are asserting that, then what are they saying? They're saying that there's something about your formula for establishing proof that they don't really believe, they're not convinced of. And I'll show you a kind of a mathematical formula for establishing proof and demonstrating assertion in just a moment. I thought it was the next slide, but it isn't. So you've got to relate your evidence to your claim in order for it to constitute proof. If not, your evidence will be considered irrelevant or unrelated to the issue. And we see these terms coming up in science all the time when we're critiquing each other. And this is a responsibility in science. We've got to be able to take the criticism. If we do everything, if we use the appropriate reasoning beforehand and we collect all the required information, then no one should be able to hit us with terms like this in discussing our research. Well, that's irrelevant or that's unrelated, or your assertion. So here's that formula for establishing proof. Proof equals the evidence plus the reasoning. So the reasoning goes into the process of making your claim, and the evidence is what you collect from the research, the investigations that you perform, and if the two are put together appropriately, then you've got proof. But if we take it back to research, if your experiments aren't designed properly such that you collect reliable data or evidence, it doesn't matter what your reasoning is or what your reasons are after the fact, you don't have proof. And there are sharp scientists out there that follow this approach and will be very comfortable standing up in an audience, however small or large, and claim that you're making an assertion rather than truly proving or strongly supporting your hypothesis. And it's not a very comfortable situation to be in. So I provide this presentation so that you get a general feel for it and can keep your guard up a little bit when you proceed to making presentations. If you hear these terms, then you know what they're actually accusing you of. Maybe they don't know the real definition of the term, but you know that how you need to defend yourself. You've got to turn back to your reasoning and back to your evidence in order to, and primarily your evidence, in order to substantiate your claim or your conclusion made on your data. So an assertion is reasoning minus the evidence, or without evidence, a claim has no support and is called an assertion. So if you don't do your experiments right, you don't test your hypothesis directly, you don't have real conclusions. You don't have any proof or evidence to provide proof for your hypothesis. You have an assertion, but everything is really messy, and it's really easy to fall into that trap. Now what we're going to do is run through an exercise in considering the types of reasoning so that we are beginning to develop at a more global level our abilities to appreciate experimental design. So this diagram illustrates the process providing reasons for your claims on the benefits of other people, and we'll proceed talking about different types of reasons. So I kind of like this one because here again in the fall of 2005, with gas prices hitting just about $3 a gallon here in San Antonio and higher around the country, it's interesting to place this claim in the context of the 1970s. So the claim is cars in the future will be more economical to run. The evidence is auto manufacturers are making cars about 500 to 750 pounds lighter each year. And your reasoning was, we all know now, 30 to 35 years later, this claim is completely unfounded. It is not supported by the reasoning nor the evidence anymore. We see some of these gigantic vehicles out there. Some of us are probably cruising around in them. And I know that mine is not 500 to 750 pounds lighter than the one I was driving in the 1970s. For sure. So the generalization, actually there's another one on gas prices. I'm forgetting my slide sequence here. The first type of reasoning is generalization, so reasoning from facts. And what we find is that we typically utilize these whenever we're proceeding to think about research, and the experiments, what is our hypothesis going to be, what do I go looking for in the literature, and those types of things. How do I frame my thoughts in order to build the background significance, the premises for my hypothesis, state my hypothesis, how do I go about asking the questions, what things do I associate with one another. So first, we can think of generalizations, reasoning from facts, and of course, again, this is from a debate book, so these would be ways that individuals would structure their arguments in a debate, whether they're going to reason from facts or use any of the other types. So here we're going to assume that if individual members of a general class of objects share a characteristic, then the characteristic will apply to all other members of the class. And we typically do this when we are beginning to talk about, to build on the significance and the background of an experiment. We try to make the case that we can generalize. There's a lot of things in common when we're focusing on this one class of, it might be, plants or animals or chemicals, or even just a general research problem. So we use this line of reasoning all the time in science. So we draw conclusions about a larger group based on observations of a smaller group of examples taken from the group. Of course, this is the type of evidence we see in public polls all the time. It's the basics of the survey research, such as public polls, and they're ongoing all the time. We experience them all the time in society. And our type of research in the biomedical field or applied biology from the biology department, we don't see too many surveys like that unless they decide to make the doctoral students teach for their stipends or things like that. And there's no formal survey, but we definitely get to know what people think. So there's major types of evidence for this. The more the examples you can produce, the better for your argument. Beyond the technique of itemizing specific examples leading you to a generalization, you also draw a sample from the total population of your subjects. And the basis of this is the basis of those public surveys. So rather than looking at every member of the population, you look at the sample and then make the assumption that it represents the whole population. So we do use this line of reasoning in science. As I said, it's rare that we're using it to set up an actual experiment or to do an actual experiment, but we use this approach to get the reader's attention that there's something in common that is of direct relevance to the experiment that I want to do or the research model that I want to use. And because others have done it, there's a large enough number of individuals that have done it, it is reasonable to think that this is a good way to do it. So the rationale for experiments. So here's the one I was thinking of. The claim is big cars are gas guzzlers, and the reasoning here is with the generalization. I assume that all big cars are like mine. The evidence is my 1972 Kingswood station wagon gets about 8 miles per gallon on the highway. Wouldn't want to be driving a car like that today, although I think the Humvees out there don't get much better than that out on the highway even. So you can see this is coming from the 1970s, and hopefully our gas mileage has improved tremendously since then. If not, you're going to be paying a lot of money at the pumps. So reasoning from facts is the form of generalization. There are tests, routine tests, for this form of reasoning. And again, I present this for the benefit of everyone to realize that there are structured approaches to criticizing every type of reasoning. And you may find that most scientists couldn't tell you what line of reasoning or what form of reasoning they're using. Is it generalization or an analogy, as we see? But they're familiar with the process and simply go down along those lines. And what we need to realize is that there are specific types of questions that can be asked in order to assess the validity of what is being presented, the claim, and to look for weaknesses, and then in science we attack those weaknesses and determine just how substantial they are and limit our interpretation of the evidence and the strength of the hypothesis based upon those weaknesses. It's just part of the process that we follow in science. We have to be the devil's advocate because that's our professional responsibility. If we overlook something that could be a weakness and just say, oh, it's not a big deal, then we're not really being as responsible as we need to be. It's probably not the most blatant ethical transgression, but it is a slippage in integrity. Anytime we compromise any of our principles and the strength or obligation of motivation to act, then we compromise our integrity. Right? So that's the way that we have to think about it and evaluate ourselves as professionals. So you ask, are there enough examples? So we see polls that are supposed to represent the opinions of people in the United States, and it's 1,500 or 2,000 people. I always question those. It just doesn't, seem feasible. And with today's technology and the abilities, it should be 20,000 or 1 million people. Then I'd feel a little bit better about it. But typically, we see that those are really small samples, and they're using this type of generalization. So are the examples typical of the whole population of subjects about which you are generalizing? So I always question those types of public polls that are expressed, slipped from 49% to 35%. What really does it mean? And then they present some index of error that has really no meaning whatsoever. What error can they calculate? I'm sure there's some statistical formula for it, but what does it mean when you apply it to the whole population? So can you account for any contrary examples? So you violate any of these test results in a fallacious argument, results in a fallacious argument, the hasty generalization, which I think happens very frequently, especially in the news media. And it probably won't change. It'll be a fair generalization for eternity. Did I just reason from generalization there? So the other point that I want to make in going through this is we see that there is a structured approach to doing science. There's a structured approach to evaluating science. There's a structured approach to studying scientists. So there are philosophers out there that they may not study each of us individually, but we are under the microscope, and philosophers and ethicists are evaluating us all the time. Nothing to get paranoid about, but it is certainly something to think about. And then the other essential part of this discussion that you need to understand is within an instant, your entire experiment and all your data can be discounted. And you can lose the entire audience, the entire readership. Typically, the readership that you will lose will be a reviewer on a grant proposal, or the reviewer for your manuscript, or a reader on your committee. So Any weakness, as I said, has to be explored, if not exploited, to determine just how critical it is. And if you fail one test of the evaluation, it is possible to have individuals become convinced at that instant that your entire experiment is discounted and they won't believe anything that you're presenting. So you fail your dissertation defense or your thesis defense or your exam, your grant proposal gets triaged and gets sent back to you with no score and no money. So these are real examples of what you are undoubtedly going to experience at some time in your career. I'm not saying you're going to fail your dissertation defense, but there'll be some point in time where a grant won't get funded, a paper won't get published, at least not the first time that you submit it, and so we encounter these experiences in science all the time. So the reasoning from a similar model or analogy, we would draw a conclusion about an unknown based on its similarity to a model that is known. So it's somewhat like a generalization that each of them uses a specific known example as its basis, whereas the generalization draws a conclusion about the whole class of objects from which, the example is drawn. The analogy draws its conclusion about another specific example. So the population polls are assumed to represent the entire U.S. population. You might perform a study on, say, a strain of diabetic rats, to go to my own experience. Then the only conclusions you can draw are on that strain of diabetic rats. You can't conclude that human diabetic patients present with the same molecular pathology, right? So that's what we're beginning to appreciate here. You cannot overgeneralize or overinterpret your data. You can, but you're not supposed to. It's too easy to do it. So the extrapolation from animal to human is unfortunately too often too comfortable for many research scientists. You're studying protein produced by a bacterium, and you're telling me about a human condition from your experiment. You can't do that. It's an overextension of the data. So here's the model for analogy. The claim is that the proposed new energy distribution agency would be wasteful and inefficient. The evidence is that the U.S. Postal Service is wasteful and inefficient. The reasoning is, from analogy, I assume the new federal agency, which is unknown, is like the U.S. Postal Service in the known areas of wastefulness and inefficiency. So at present in our society, again with the issue in New Orleans of the Hurricane Katrina and the flood, is the questioning of the efficiency of the entire U.S. system to respond in this type of a national emergency. So we see this type of debate going on all the time. So the old FEMA to the new FEMA and all the new types of homeland security agencies and all types of criticisms. So the test for an analogy is this. Is the unknown example like the known example in the essential areas being compared? So as long as the similarities lie in the areas about which the claim is made, argument by analogy constitutes proof. If the analogy draws its comparisons in an area not relevant to the claim, the argument will be faulty. So it's not unlikely to encounter a criticism of your research where someone states that you have presented a false analogy. So it's important to try to understand how reasoning by analogy occurs. And then finally, the cause-effect. And I like this progression because you will find many researchers claiming a causal association for their experiment when the experiment really isn't designed to test the cause-effect relationship. So again, we start presenting it here at a more conceptual and abstract level, and we continue to pound on this cause-effect relationship in science. It's the ultimate goal of science to be able to claim that I did this to my independent variable, and my dependent variable changed as a cause of that. It is an effect of the change in the independent variable. And we will go through the process of determining exactly how cause-effect relationships are established in science, and hopefully develop your skills in critically evaluating someone's claim on their research. Many people claim a causal association, and their experiment just isn't designed to establish it. And it's a key fault. And as soon as you find, if there's a scientist, all of their reports tend to take that final leap, but they never really look to do the final experimentation or have the discussion tempered in such a way so that you appreciate the limitations of interpretation of their claims. Then you begin to discredit all of their data. They may be collecting beautiful data, but because they overextend it and push it so far, you begin to lose your respect for them and question their integrity, and you begin to discount their contribution to science. And it can happen to you if you don't appreciate what you are doing. I had worked with a scientist that loved to do this, and I argued and argued and argued and argued and argued and never could convince the person to see my point of view, that they were not establishing a causal association, but they were claiming a causal association in the discussion. So it can happen easily. So reasoning from the process of the process relationships. A cause-effect relationship is one in which two phenomena, objects, events, are observed interacting together in some process, and it is assumed that one of them causes the other. So it's a simple statement. We all know that. And the form of the argument is if-then. If I manipulate or alter my independent variable in this way, then my dependent variable will change in that way. And I'm just throwing out independent and dependent variable, kind of teasing you if you remember what they are. Those of you that are working in the laboratory or have an extensive experience probably recall what they are. At a later time, we begin talking specifically about that for research design and graphical presentation of data and statistical presentation of data as well. So we're going from a general to a specific as we proceed through these lectures. So reasoning from process relationships. The claim, my heating bill will be outrageous. This is the coldest winter since 07, so this is 1907 on here. We're in 2005 now. We're just two years away from a century on that one. So we have to put it in perspective now. We can't even use 07. We've got to say 1907 as we're in the 2000s. So the reasoning, cause effect. I assume my furnace will burn more fuel than usual because of the cold weather. If the temperature goes down, then my thermostat will kick on the burners. So it's kind of a non-scientific example, but this year, again, with the increasing price of oil due to everything that's going on in the Middle East and in the United States right now, you can be sure your heating bill is going to be outrageous this year, just as your gasoline bill is to drive your vehicle. And they're expecting one of the coldest winters, so people up north are going to be in very, very severe, dire situations. We know that it's coming. What are we doing about it? Probably nothing, because right now there's such a focus on what's happening. So we have to use our theological ethics and pray, basically, that no more hurricanes hit the United States and cause more devastation as we wind down the fall and head into the winter. It could be a tremendously worse year than we had ever had before. So those of you that are watching this 2 or 3 years from now, look back on the history and see how we did. Continuing with the cause-effect then. The cause-effect relationship assumes that in the process of interacting, there is a connecting link between one phenomenon and another. This connection is so strong that the relationship is predictable. So now we're beginning to see the scientific part of it. And hypothesis is a prediction. So we tend to set up our hypotheses in the format of a causal association. I want to establish a causal association. If you don't design your experiments properly and carry through all the appropriate analyses and make sure that you satisfy a sufficient number of the criteria, you don't support your hypothesis. If you state it strongly enough so that it reads as a study of that is going to establish a causal association. So that's why I felt it was important to look at these generalizations on the matters before we just jumped into the research part of it. So as long as other factors involved in the process are unchanged, so we have to control all the variables that we can possibly control, the results of the interaction between the two phenomena will be the same every time it is repeated. So the repeatability of research is extremely important, and that's a point that's brought up by the authors a few times in this chapter and in the prior chapter as well. We have a responsibility as scientists to make sure that other people can repeat what we have done. And there's a variety of ways of doing that, and we're going to look at them all very closely as we proceed through this series of discussions. So there's also situations in which two phenomena interact together, but not by virtue of a causal link, but by sheer coincidence. So we're going to talk about this as we proceed, so I don't want to spend too much time explaining it here, but we all know that. You could just be observing two independent phenomena, and they have absolutely no direct relationship or link with each other, and we should understand how that is a weakness in science. It should not be repeatable. You should not be able to get statistically reliable differences if there's no actual link between the two. And we will build up to this discussion and presentation of the range, the continuum of strength of linkages between our independent variable and our dependent variable to get very specific. And the strongest linkage, of course, is the causal association. So coincidences have that quality of unpredictability. If you try to repeat it, chances are you're not going to observe it reliably. It's not going to achieve statistical significance. So many words of saying the same thing. So they're in the realm of the possible, just barely, but not in the realm of the predictable. So sometimes, it's actually rather frequently, trainees in research laboratories that are doing a master's thesis, undergraduate honors thesis, or a dissertation will do a pilot study and collect 2 or 3 data points and try to use that data as their preliminary data to strengthen their argument to go on with the experiment. And it can be very easily criticized in that with that few observations, you still may not have a strength of predictability. There still is a chance of coincidence. Why? Because you probably can't perform statistics or get a strong statistical relationship or probability with a small n, and you don't have a strong predictability. So there's 2 approaches that we'll look at when we get to that point of looking at research design. That is estimating the sample size, the n, and doing a power analysis to look at or predict the strength of the distinction, the difference that you might observe between your treatment groups with the N that you propose, the sample size that you propose. So here's this general building up to the specific, and it just provides us additional opportunities to hear and see the same trend of thought in being critical about establishing proof. So they are in the realm of the possible, just barely, but not in the realm of predictable. So the notion of intervening variables. So this is a term that I'll begin to use as we proceed, and the intervening variables will take on two other terms, confounds and bias, as we proceed. And that's pretty well all-inclusive. There's a couple different types of biases that we'll define and discuss. So what makes, so it's the notion of the intervening variables that what makes the cause-effect relationship problematic. You know, so you think you've got it, and then somebody will come along and say, well, did you control for this, or did you measure that, you know? And it's very frustrating because all of a sudden you can realize that you missed a key point. Too late, the experiment's done. You virtually have to repeat it if it's that important. From a purely scientific point of view, it is next to impossible to fix a closed system with only two components operating in an unvarying process of interaction, totally immune from any outside variables. So that's why it is critical for us to study the bias and confound as part of experimental design. So there are other linking relationships less powerful than causality, which could exist between two phenomena. And we can imagine a spectrum or a continuum ranging from zero linkage to total linkage. So we see on this table below zero linkage on the left and 100% linkage on the right. And it spans from coincidence to causality. And we'll talk about each of these in general, but I'll just quickly go through them here. So the coincidence is an expected outcome is highly unlikely. Can't make a prediction. Association, it's plausible or possible at one level. And we'll see that what we have to do to get past this point or to establish that there's an association is rule out chance. We hear chance, we should think immediately of statistics. Has to be a statistical test to proceed through this. And this is what we're going to talk about when we go through experimental design. How do we proceed along this line to end up with the study and data that can establish 100% linkage? And we'll establish some terminology and definitions as we go along as well. Correlation, probable and within a confident high level of predictability. So we all know that there are mathematical statistical formulae to test correlations. There's many different types, linear correlation and nonlinear correlation, a whole variety of statistical tests that can be used to test for correlation. And it's not all that uncommon to read a research article or even in writing on some of your own studies where you didn't perform any correlational analysis, but you say this is correlated with that. You can't say it. If you didn't do the mathematics, if you didn't design the study to test for correlation, you can't say they're correlated, right? You can say that I ruled out chance. They're statistically significantly different at a p less than 0.05. Great. You showed me that there's an association. If you dare to go on to say there's a correlation or a causal association, I'm going to slap you down in an instant. So the causality, of course, certain and totally predictable. So if you can establish causality, anybody that repeats it should be able to do this, and it will cause that directly. But we know that it's more important than that. You still might be able to have some thing in between that, well, we'll talk about it here. So the concepts of association and correlation allow you to reason about the relationships between phenomena and is still taken into account the intervening variables. So there can be variables controlled to one degree or another. Those controlled to a lesser degree really are a major weakness, but you still can proceed along that continuum of linkage from a 0% to a 100%, from correlation, from coincidence to causal association. So the association linkage merely establishes that where one phenomenon is found, the other is likely to be found. So passing a statistical test doesn't really mean much. And a lot of science, probably the bulk of science, is limited to this. Did you perform a statistical test? Yes, I did. It was significant at p less than 0.05. So what? What else did you do? Enlighten me, right? So a lot of science is actually weak because it stops right there at statistics, does not proceed to correlational analyses or to satisfy the criteria of establishing a causal association. He's been up there all this time? He doesn't know he's there. Let's just go to local on both. So here I am lecturing to you, and you're more interested in watching some guy who's somewhere else. I thought you were all looking over there to get a better example. Now I've got it messed up with it. So those of you that are viewing this through streaming video, you'd have to be here to appreciate it. Sorry about that distraction. So the stopping at mere statistics is unsatisfactory. We have to accept that. So no attempt is made to prove that the one causes the other. In fact, in this instance, the two phenomena may not be directly related anyway. It rules out chance. It means that you have an association. If you repeat this and you observe this, there's a strong probability that you're going to observe that. But if I have gone further to prove that there is strength in the argument of causality, then I have a more direct predictability. If you do this, you're going to see that. So rather, they each may be closely related to a third factor, which could be a horrifying nightmare, where the third factor is somehow involved. And so if there's any variable that you cannot control or haven't controlled adequately that affects that third factor, you're not always going to see the same magnitude of effect when you change your independent variable and measure the change in your dependent variable. So correlation linkage is stronger than the association linkage. Not only are two phenomena typically found together, but they vary together. And it's quite obvious to show that, or to realize that establishing correlation, it takes more experiments because you've got to have more data points. But if you establish a correlation, then you're one step closer to the causal association. This is pretty strong. As I incrementally change my independent variable, my dependent variable changes in an incremental way, in a predictable way, and magnitude and direction. So we're getting a much stronger argument on the association between our independent and dependent variables. So not only are the two phenomena typically found together, but they vary together. So that is, changes in the scope or magnitude of one is accompanied by corresponding changes in the other. So this brings us to something that we should recall readily. When one phenomenon increases and the other increases, the correlation is called direct. When one increases and the other decreases, the correlation is called inverse. So let's go to our document camera and remember that. So let's use, this time I've been helping my daughter with some of her physics. Surprising what you can kind of remember from so long ago. Velocity equals distance over time. So velocity is directly proportional to what? To distance. And velocity is indirectly proportional to time. So that's basically what we're saying here. So we know that if we graph distance and time, then we will have a reflection of velocity, and that velocity will change, will decrease as time increases. Velocity will increase as the distance increases, as long as the other variable is held constant. So there's a lot of things like that that we know, don't always remember and put to use, but that's basically what's saying here. So we should be able to analyze our data in the end after performing a correlation to be able to say that as I incrementally change my independent variable by doubling the concentration 10 times, the dependent variable decreases in a direct relationship. It's directly proportional to that. So we sharpen our understanding of the terminology so that we can be critical of other persons' claims. So the traditional tests of the cause-effect reasoning, there are two standard questions to answer about any causal link. First, is the cause necessary to produce the alleged effect or effects? When we talk about establishing a causal association in science, we'll have other criteria. These are, again, from the debate. So, are they necessary? Is it a necessary relationship? Or is the cause sufficient to produce the alleged effects? Obviously, sufficiency is a little weaker than necessary. So other factors may intervene in a complex system to alter the outcome. This condition is sometimes described as a multiple causation system, where one factor may be part of the effect but still insufficient to produce the effect by itself. So that third factor might need to be present. If you just targeted the third factor through some other means, it may not bring about the result that you were observing. As well, the observation wouldn't occur if you didn't have that factor 3 there. So it is sufficient. Factor 1 depends on factor 3 to bring about our observation on factor 2, and therefore factor 1 is sufficient to cause the change that we observed in factor 3. When we find a difference between the groups, we must consider the possible explanations for this difference. So there might be a spurious association. So this is the difference in the due to the difference in the groups that's due to non-comparability. That is a difference in the composition of the groups. So when we define the different biases, we'll use these same terminologies to discuss bias. This association is the subject bias and confounding. So the subject of bias and confounding, as I said, when we get there. So you might have a non-comparability as an argument that you're making just a spurious association. Remember, the spurious association is ruled out by chance. The chance association is the difference in the groups is due to chance, and this association is the basis of statistical analysis. Excuse me, I need to back up. It's the control of our variables other than our dependent and independent variables that rules out the spurious association. Sorry about that. Obviously, we rule out chance association by statistics, as we just stated in the other slide. So when we control our biases and our confounding, and we're sure that we've got a comparability of our data, our treatment groups, our experimental groups, and we've controlled all the variables that we can, and we just use our dependent and independent variables, then we rule out the spurious association. So a well-controlled experiment rules out spurious association. Chance association is ruled out by statistical analysis. What would you observe in your data if you did not control all of the bias and confounding? Picture a graph. Put all that stuff back there. If you picture a graph, say that we have a bar graph, 2 bars. What's missing from these bars to interpret them? Error bars, right? So if you don't control for confounding and bias, what effect will there be on your error bars? If you have low level of control, what will be the effect on your error bars? It's going to be huge, right? So if you see data like that, first the error bars overlap, so you know that they cannot be statistically significantly different. But something happened in this group where they didn't control for the variables, the bias, and the confounding as well as they did in this group. So that means there's something wrong there. These are non-comparable. You can't make any comparison between these two, right? So in so many words, we really are capable of visualizing what we're seeing on the screen here. So spurious association, we control our variability. Chance association, we got to perform the appropriate statistics. With just the 2 bars that I showed, probably do a student t-test, right? It's not enough data to demonstrate a correlation, so you would have to stop there and be tempered in limiting your interpretations of your data. So the difference in the groups is due to true causal association between the test factor and the outcome. So this is now what we're going to be talking about, basically independent variable and dependent variable. So the test factor and the outcome is going to be our terminology now. You've got a test factor that you can play with, your independent variable. The experimenter can change that independent variable. And the outcome, the dependent variable, your observation. So the test factor and the outcome. And then there's going to be intervening factors, which are the variables, and we'll define them under in the context of bias and confound. So in order to prove our hypothesis and conclude that the last explanation is correct, that is, that the test factor led to or caused the outcome, we must first rule out the other 2 explanations. So we must rule out spurious association. How? By controlling our experiments, having well-controlled, tightly controlled experiments. We rule out chance association. How? By statistics. And then we proceed then to establish correlational association and satisfy other criteria that we'll talk about in more detail later to satisfy the requirements for proving or strengthening your claim that you have a causal association. And then we'll just quickly go through this discussion of statistics, the reasoning from the scientific methodology. Even though we know we've mentioned it, these authors somehow had a separate presentation for it. So the findings of any scientific study must be strictly limited to the population tested, right? So if you investigate a rat strain that develops diabetes, you don't make claims about humans and their conditions of diabetes. You can speculate, but you can't draw conclusions. So under the conditions which prevailed during the test, it is contrary to the scientific method, so therefore we have preclinical and clinical trials for drug testing to treat human diabetic patients. So it is contrary to the scientific method to make extensive extrapolations of the findings of a strictly limited study into realms where those do not apply. So we're all capable of thinking of examples there. Here's the one they gave. The solar energy is not the answer to the energy crisis. The evidence is that the studies show that solar energy is economical only as a supplement to a regular heating system, only for heating water, only in certain geographical areas. The reasoning is statistical. I assume the methodology of the studies meets the scientific standards, and we're going to establish the scientific standards for evaluating studies with statistics and for evaluating statistical approaches to study data or analyze data. We're not going to become statistical experts, but we're going to work with that idea. So whenever reasoning is based on a method of statistical analysis, the important thing to remember is that what is claimed is not based so much on the results of the calculation as it is on the quality and the limitations of the method used. So you can never take a strong stand on just the statistical test that was used. You have to fit it into the whole framework of the method. If you collect messy or dirty data, the statistics can't fix it. The calculations themselves are truly only insofar as the methodology used is a good methodology. So garbage in, garbage out, statistical methods that are not commonly seen are typically received with great hesitation and trepidation by scientists. Very few scientists are statistical experts. We have a realm of statistical procedures that we're comfortable with and understand how to use them, and turn to statistical experts when we feel we need to. And we see a new strange test in the literature that we don't really understand, we begin to discount the evidence almost immediately. Why was a different test used when this test is most commonly used? So the authors deal with that in some detail in this chapter in the textbook. It's also important to know the assumption used in conducting the experiment, because small variances in those assumptions can produce large variances in the calculation, as we had said. We see the error bars on a graph. If they're big, we know that the experiment either was not or could not have been controlled well enough to limit the variability. Some experimental procedures, you can't control enough of the variables to get real tight error bars. You just have to live with bigger error bars. Therefore, it makes little sense to test the results of the calculation without first examining the assumptions used in the methodology. Your experimental design, actually the background and significance statements to build up to the claim, your hypothesis, the premises for your hypothesis, are just as important as the statistics. Those are just as important as your experimental design, the rationale for your experiments. Why did you use that concentration of that compound? Has anyone else used it? Have other scientists used it at different concentrations? So what's the relevance of their choice to your choice of the concentration or the dose of the drug or the microbe to be used or the plant cell type to be used? So all of those assumptions that are made from the first word up to the point of collecting a set of data are just as important as the calculation you use to analyze it, because the calculation can't fix a problem that came before you put it into the calculator, right? So this brings us then to something a little more specific, that we recognize a theoretical framework. So when you are asked to write a grant proposal or a research proposal, you are told to put together the background and significance and to point out the gaps. So this is, I just kind of put this together for us to evaluate it that way. So in a theoretical framework, and I look at theories as something like a bigger picture than a hypothesis. A collection of hypotheses, whether they used to be hypotheses or they're still hypotheses, doesn't really matter in this definition. It's a collection of hypotheses that put together a bigger story, and that's a theoretical framework. So the theoretical framework is generated in your background and significance section, where you state facts. So some things we simply accept as fact. There will be gaps as we tell this big story, and there can be strongly supported hypotheses, 1 and 2 shown here. Here's another gap. Or weakly supported hypotheses, and other facts. So I'm not going to try to put together an example because on my feet I'm never very good at it. But we all can picture this. We tell a story about a specific scientific problem, a biological or medical problem, or environmental problem. There's some things that are established as fact. Nobody questions them. There are other things that are strongly supported, but we don't quite see it as a fact yet. There are other things that fit into the big picture that, we'd really like to see a lot more work done on that. And then there's just big holes. We don't know what is going on in this part of the entire problem. So from the perspective of succeeding in science and meeting the expectations for as an independent researcher with the National Institutes of Health, you're expected to point out gaps and come up with a new hypothesis, have the rationale and experimental design to test the hypothesis. If the hypothesis is supported, it gets put back in to fill that gap, and then other approaches to test that hypothesis or a different way of framing the hypothesis will build on it so that ultimately it becomes a weakly supported hypothesis, and then strongly, and then hopefully finally a fact. If you establish a causal association with very extensive series of experiments, it can almost zip straight to the point of being a fact. Certainly go right to the point of being a strongly supported hypothesis. But this is what you are expected to do to be an innovative, independent, unique scientist in the world today. If you chase down weakly supported hypotheses and come up with new experiments to test them, or using new methodologies or generating new data, then you're not viewed as being a very strong scientist and shouldn't expect to be too awfully successful. I've forgotten the exact wording by the authors. I think they said you either crash and burn, or it's not really in this context, but they're in their discussion, either crash and burn or win a Nobel Prize, right? They're using it in the context of questioning the standard scientific approach to doing things, which is what we're talking about here, standard scientific approach. But it is possible throughout your research career to pick on a weakly supported hypothesis and, after making significant contributions maybe, and use this approach. It's not invalid, it's just in the context of science in a society. Because if it's weakly supported and then you perform experiments with new methods or generate new data, and it's not supported, it gets knocked out of there, and you have a renewed or refreshed gap for which you can begin to ask new questions. So in the next lecture, we'll talk about hypothesis and proceed from there and begin to talk about research as a concept, asking the question, what is research, and to look at the scientific method really from the perspective or the terminology of the research method. So I appreciate your time and attention, and remind you to check on the WebCT for the case studies, because they're beginning to get posted now, by me at least, and hopefully soon you'll begin to find the ones from the textbook that you would like to present and begin scheduling them and taking responsibility for them through the calendar and the discussion portion of the WebCT. Thank you.